Alright, so we're going to start by saying that we have these two discs here. We have disc 1 and disc 2. They're going to be of equal mass, and they're both going to be connected on this string. This is a string, not like metal or anything, so it is flexible. And that's connected to another string, which is being pulled by a force F. Right, and we'll see how it ends up is that as F is going, these two discs will become closer and closer together because those strings just, they pull, and the balls will just, or the discs themselves will get closer. All right, so the what I have here labeled is that our length L is going to be the change in center of mass, because if these are equal of mass, the center of mass is going to be right here, which I just kind of drew down here, and in the ending our center of mass is going to be here, and I also just drew that down. So our distance L is going to be just the change in the center of masses, and it's written as a vector. And our D is actually going to be, for a further part of this problem, it's our extended system, because as you can see, the force will go much further because there is the distance right here that the strings did move, which gave the force extra length, I guess. Alright, so the question that we actually have for this is, what is the change of internal energy of this system? So we're going to start just kind of with, different energies altogether. So we're starting with the point particle system, because that only involves our translational kinetic energy. And to find that, you have to do the net force times the change of center of masses. And I do just have it as R. I'm not really going to get into all the numbers, but both of those are vectors, so we do have to write that as a dot product. And there is nothing moving in the Y nor the Z direction, so if you wanted, you could just write it as F of L. Alright, so our change in translational kinetic energy is just F of L. Now to move to our extended system, I did consider it the real system, because it will have the translational kinetic energy, plus we're doing that internal energy, which is, thermal energy. So it's not point particle, because it does have more than one. Alright, so in our extended system, we do have, like I said again, that difference right there between the force and our length of masses, L. So that new distance that we have is going to be D, which is the length of the ends and the beginning of the force. Alright, so our change of energy altogether is going to be the sum of all the work. For a real system, the work has to be the work done on separate things. It's not really all together. However, there's no gravitational potential energy or frictional energy. We're not talking about any of that. We're simply just doing the force of that one thing being pulled. So our sum of work is only going to be the work done by that force, which is just going to be the force times the distance. And our change in energy, like I said, is going to be the translational energy plus the thermal energy or internal energy, same difference. Once again, the F times D is going to be both vectors, so you can write it in vector notation, or since it is just in the x direction, you can just write it as F times D. Alright, and I don't know if you remember, but we actually already solved for our K trans, our translational kinetic energy. It's just F of L, so I did sub that in right here. F of L plus the change in thermal energy is equal to F times D. And to put thermal energy by itself, you're going to subtract F of L and subtract it over here as well. And what you'll be left with is the change in thermal energy is equal to F times D minus L.